Good evening and thank you all for joining us today. My name is Rashmita and I'm the event planner for Microsoft Reactor Bengaluru, India. The session will run over the next 60 minutes, including Q&A. The session is being recorded and will be uploaded to our Reactor YouTube channel. I will share the link to our YouTube channel in the chat section soon. Before we begin, please take a moment to read our code of conduct. We are all here to learn together, so please be respectful of other people's views, understanding of differences, being kind and considerate in the way you engage. The chat will be open throughout, and we do encourage you all to participate. Also, please keep your mics muted during the session. I would now like to welcome Shivam, our speaker for today's session. Shivam is an author, cloud architect, speaker, and co-founder at TechScalable. He is passionate about technology and works on Azure, GCP, machine learning, and blockchain. He is also a Microsoft certified trainer. But for now, I will hand over to Shivam to begin the session. Over to you, Shivam.
Thank you, Rashmita. I will share my screen. Okay, good evening, everyone. Hopefully, all of you are doing well and you're safe at home as well. Now, I will just walk you through the agenda for the day, like what are we going to discuss, and then we'll get started right in a couple of minutes. So check this out. The topic for the day is distributed deep learning. And when we do the distributed deep learning, the framework will be Horovod, and we will be using Azure Databricks to do that. Now, there is a particular learn module which is there, and this learning module, which is for further learning, is already there in the chat window as well. And it is something which I will just copy from here and will open up to show it to you. So like what to do once we go through the session. I have also pasted a link in the chat in case you want to keep it with you. Now we will be discussing about lots and lots of different type of concepts. We will be so the library or the framework which we are using today, it is created by Uber. So there is a history behind that, like why it was created, what was the reasoning behind it, and so on and so forth. So all those elements and concepts and fundamentals we'll cover. But after the session, in case you want to go through it again or you want to have a more structured way of learning, in that case, you can come to this page over here. You can even sign in from the top using any email ID which you have, and then you can simply go through these modules over there. So I'll just give you a walkthrough of it, and then we'll get started. So there is an introduction over here. Then the what is the meaning of the framework which we are using, Horovod as such. So why it was created, what was the reason behind it, and how does it work, and what is Databricks, how do you work with it, and then so on and so forth, right? And then what is this HorovodRunner? So in Databricks, which is a Spark cluster, we use HorovodRunner. We'll cover it, but all of those things are also mentioned on this in this learn module in a very systematic and structured way over there. So we will be going through all of this, but you can also do it later on as well. If I click on the exercise, there is one hyperlink over here which will take you to the DBC notebook, the Databricks notebook, where the code is available. So in case you want to reproduce what I will be showing you, you can totally do that from this learning module, which is there in the chat. Now, so let's get started, right? So the topic which we are covering is on Horovod. It's a basically a library which is created by Uber for distributed learning. So we will first understand why it was created, like what was the problem which Uber was facing, and how did they resolve it. So what did they thought? What was the reason behind it? What were the practical problems which they faced, and what are the fundamentals, elements, and so on and so forth of their problem statement. So when we will go through that, we will realize that uh, there is a very natural evolution which has happened in the distributed framework. as such. So we'll be able to get a better hold of the technology, and then we will understand that when you run this on Spark, there is something which is totally new, which needs to be understood. So we'll understand that part, the barrier mode over there in Spark, and then we will practically see it. Okay, so let's get started. Now, there is a so Uber before Michelangelo is the learning platform, machine learning platform of Uber. Just FYI. Now, any picture which you see over here, I have taken from Uber's blog only, and they had the total credit of creating such nice images over here. So, anyways, the Michelangelo is their learning platform, the machine learning platform. Now, before they created Michelangelo, they started making it in 2015. Before they created that, nothing was systematic as such. The data scientists were creating using different type of programming languages also, and they were using different type of algorithms as well to create the various models. Now, one thing which Uber themselves let us know is that before they created Michelangelo, the they were limited by the models which were trained locally on the systems of the data scientists, and these data scientists used to have the development desktops were there, powerful development desktops were there, but that's where they were doing the model training, and there was no systematic approach, there was no pipeline to be deployed, there was no pipeline using that which we can deploy the model into production. So the data scientists at Uber, they were using all the different open source technologies to make things work. So, and there was also no data store before it. So they started working on Michelangelo in 2015, and this platform basically got created as a result of that. Now, the this platform Michelangelo at Uber is something which they are extensively using in all the different type of services which you use. For example, in Uber Eats, they we have like there are various type of predictions which are going on. The ranking of the restaurants are going on. Delivery time, the estimated delivery time is being calculated. Search ranking, and the search autocomplete is going on. Now, it is not that easy. If we just try to understand the problem statements which they are facing is, so let's say you place so let's say this is where you are, and you have placed one order. You simply opened the mobile app and you have placed one order as such. Now, the entire process is pretty complicated because the based on your order, that time will be taken by the you can say the restaurant as such, and they will be cooking your order as such. So it might take some X amount of time for that. So that is one of the moving criteria which needs to be understood. Secondly, the the rider or the driver who will go and pick it up, right? So when they go and pick it up, they are supposed to reach over there when the food is ready, nearly when the food is ready. So they are supposed to reach at the optimal time or at the best time itself. Now, when they reach the location to pick up the order, it is also possible that they don't find the parking spot for parking the car. They have to get out of the car, they have to go inside the food place, and they have to pick up your order, come back and start, and then drive to your location. So there are too many moving parts as such. So they so what Uber did, Uber created this platform Michelangelo, and it is basically divided into two sections. There is an online system, and basically it is having offline part over there. I'll further zoom in, right? So the online part is something which is getting the data from some of the real-time system, some of the real-time production systems in Uber, and the data might be coming from both the mobile application of the driver and also from the mobile or from the car itself, like the vehicle itself. So they have logics around both of them. So they get online data, and they are using Kafka extensively. They are using Apache Samza, which is basically an stream analytical solution. And For the offline mode, they have HDFS based data lakes, and on top of this HDFS based data lake, they use Apache Spark. They have one thing which they have mentioned in their documentation is that by storing the features, this is something which is very useful for the team. Like when they were able to create the extra features and they were able to store it, the other team members were able to utilize that, and they were able to create, you can say, were able to train better models. They were, and the time also reduced. So they at any point in time they have around 1,000 extra features created on the data and saved in the feature stores over there. Now, apart from that, they do both batch training and real-time predictions as well. And they also store the metadata in the Cassandra-based model repository. So earlier, before Michelangelo was there in Uber, there was no model repository. So now, but they have this metadata-based repository now, where they store the information about who created the model, which algorithm was used, what were the criterias, what was the hyperparameters were used, and so on and so forth. All the logics around that. Now, why we are discussing about this is one of the component of Michelangelo, the deep learning the deep learning toolkit from Uber, Michelangelo, this platform from Uber. One of the component of this platform was open sourced. That component of this platform was called as Horovod, and that is used for distributed deep learning. Now, if I just take you further into the some of the pictures which I have taken from various, I have taken this from a white paper, it seems. So now whenever you talk about big data and machine learning, there are so many problem statements. It's not easy as such. Like, anyways, deep learning is anyways itself supposed to be not that straightforward. But when you combine that with data, with big amount of data, and with velocity, variety, and volume, then things become even more complicated as such. So data collection systems are there, feature extraction is going on, machine learning needs to be to happen, the analysis tools will be there, the resource management tools, some sort of serving infrastructure and monitoring services should be there. So what Uber did, so when they were creating Michelangelo, at that point in time, Facebook created one execution mode where Facebook basically, we can say, started there's an execution mode called as data parallel execution mode. So which Facebook started, they even they have even published one white paper on that. So that white paper was used by Uber. They got motivated by that. They understood that the so what is this data parallel mode? Basically, if you have data, you can, for example, I have let's say 3 units over here. So let's say one partition of it or one chunk of it is being processed here. One chunk is being processed here. One chunk is being processed here. So you distribute the data across various nodes and operate on the data in parallel. That's what that means. Now, so the logic behind Horovod is like, is it how much fast can we do it? How easy is it? Is it easy to convert the existing code into something which can be executed on in parallel, or what is the complexity level of that? Now, so motivated by the data parallel approach of by the from the white paper published by Facebook, what Uber did is, uh, before I go there, I just want to show you a couple of things here. You see this, the model is training. So there are three different locations where the three different worker nodes are there, where the model is training. One chunk of the data is here, one chunk is here, one chunk is here. Now some gradients are being calculated, and average gradients are being calculated here, and then that is the one which is being used for any weight change over there, or for any optimization or the parameter change as such. It is happening having like, you can say, the average is being used over there. So at that point in time, Uber was using TensorFlow distributed. Now TensorFlow distributed is great, but TensorFlow distributed uses parameter server for the purpose of distributed deep learning. Now what parameter server does, like if I have, for example, let's say we have 3 workers. So the purpose of that parameter server is to find the average of the gradients, which are being like getting trained on different worker nodes right now. So now if we have one, so these whatever I'm telling is like the observations of Uber. So what Uber observes over here is that there are two problems which they found when they use TensorFlow distributed. So the two problems were that the ratio of the parameter server to the number of worker node was one of the problem. The second problem statement was around the complexity of the code. When they started using TensorFlow distributed, and they started converting their existing code, that became very complicated. And a lot of time because of the you can say this is something which is known about TensorFlow, right? It is, for example, TensorFlow versus Keras. Why was Keras more so popular? Because Keras used to have less amount of code to do the same thing, right? Sometimes it becomes little more options are there, so it becomes little more complicated to work with it. So now they have there are two straightforward points which they have mentioned. First is that in case we have, let's say, one parameter server, then it will be a single bottleneck. It's a choke point over there. Like one server is there and it is doing the, everybody is talking to that one server, and that one server is finding the average of the gradients, and then it's you can say responding back or distributing the gradients back. Second thing is if we have lot of parameter servers, right, like this. So over here they have 3 and 3. Now, in case they have a lot of parameter server, then it becomes an all-to-all communication. So too much of traffic, too much of data, you can say too much of parameters or too much of, you can say literally data moves over the network, and it becomes extremely difficult, or the network gets choked over there because of all-to-all communication. So this is what Uber was facing as such when they were using TensorFlow distributed. At that point in time, uh, in China, basically Baidu, what they did, they were working on the HPC, high performance clustering or high performance computing. It's basically parallel computing with deep learning. So they created one, they released one white paper on it, uh, and this is something which Uber also found very interesting. So what in this white paper, basically there was one approach which was introduced called as ring all reduce approach. Right. So let's have a look at that ring all reduce approach, and then we will understand what it does, right? And this is the one which we'll finally use. This is the one which Horovod will finally take forward. But if you check this out, the problem with the previous approach was that if we have less number of parameter server, then too much of it becomes a bottleneck. If we have too many parameter server, then everybody is talking to everybody, and the network doesn't is not utilized properly. So for smaller type of model, it may be okay, but for when you're training any very on a huge amount of data, when you're training a deep learning model, this will become a problem over here. So in the white paper from Baidu as such, they have introduced this ring all reduce. What it does is a very simple mechanism, but it's very effective as such. So imagine there are three. Just have a look at it. Don't even need to imagine, right? So we have these three workers right now, right? And there are some data points inside it. Maybe a tensor is there having some values inside it. This example is just for you can say explanation purpose. So there are some you can say data inside it. Now in the ring all reduce approach, the one node will be talking to two of the nodes which are near to it. It's like you're creating a ring and you're talking to your friends, and so on and so forth. So this will get you can say added to that or multiplied, or any operation will happen on top of it. This will get added to it, any operation will happen, and so on and so forth, over there. And this basically will you can say uh, get reduced by the third option. So this type of ring approach happens, and this cycle keeps on rotating. So what I have created over here, if you just look at that, right, the green part. So that 5 got added to that 8 over there and became 13. This is just to explain that how it is working, right? So 13 got added to that 11, it became 24. Similarly, 4 and 2 were added to this 3 and 15, 7 and 17 over there. And then we have 8 and 4, which basically got added to 42 and 1. It became 50 and 1, 50 and 5 over there. So then the process keeps on repeating over there. You can see. Then the next value get, you can say, is it's transmitted, or communication happens for the next value as such. Then in this ring approach, the next value, then the cycle again repeats. See, then the cycle again repeats. So finally, what happens? All the different worker nodes which are there, they are able to get the value of the parameters as such. Now, this is something which Uber found to be very useful for them, because in this approach, the network was being utilized in the optimal manner. It was not getting choked. It was getting optimized in the best manner. So they picked up two things from here. So from the Facebook's you can say white paper, they picked up the data parallel, the execution mode one. And from this white paper over here, they basically understood that ring all reduce approach is something which is very useful. So what they did, they literally took TensorFlow distributed, and they created their own modifications on top of it. Now, before I go into all of that, there are a couple of things which I want you to remember. We will be using these words in all the location. So the communication which happens between these multiple GPU cores or these various processes, this is so this is basically called as message passing interface, MPIs. Now MPI will be having a couple of things which we have to understand. All reduce without ring, we just understood the ring part. Like if I don't have the ring part, then how will all reduce work? If there are multiple processes which are running, for example, we have this 0, 1, oh, sorry. So I have these multiple processes over here. Let me find that again. Right, you see this? Let me start from here. So what we have over here is basically we have 4 servers with us. Right, there are 4 servers, and every server is having 4 GPU right now. Just for the ease of the explanation, I have kept it 4 over there. So 4 servers and 4 GPU. So total number of processes which are there will be 16. Let me just quickly see. Let me just try to make it slightly smaller. Let me just quickly arrange it so it doesn't do that again. Okay, let's go back. Okay, now check this out. Now hopefully this time it will not misbehave. So we have 4 servers with us, and 4 servers are having 4 GPUs. So total number of processes which we have will is over here, which is called as size. So in the MPI concept, in the message passing interface concept, there is one of the element. If you want to learn it, you have to understand the concepts over there. So if somebody says size over there, what's the meaning of size? Size is basically all the processes which are there. So right now we have 4 into 4, 16 processes. So size is 16. Now, there is a concept called as rank after that. Now, I have 16 processes, 16 minus 1. So there are 15 unique IDs are there. It will start from 0. So 0, 1, 2, 3, 4, 5, 6 till 15. So 16 unique process IDs are there. So that is called as rank, right? Remember this. So size is the total number of processes which we have. Rank are the overall uh, process IDs, the unique process IDs. Now, there is another thing called as local rank. So inside one server, this is applicable to inside one server. So we have 4 GPU inside that one server. So we are calling that. So this is GPU number 0 over here. This is 0. This is 1. This is 2. This is 3. So the local rank is 4 right now. So it starts from 0, 0, 1, 2, 3, like that. So we have, this is the unique process ID inside the server. So there are 3 concepts we have to remember, that we have a size. Size is the overall number of how many processes do we have. The IDs of that will be the rank, the unique IDs, and the local rank is on the server level on one particular server. So if I just take you to the other concepts, so apart from these 3 things, and apart from the ring all reduce, there are other concepts as well, which I have written over here. Today, we won't be using anything else apart from the ring reduce, but just for your you can say knowledge purpose, you can have a look at this. So right now there are 2 servers right now in this example. The diagram will become very big with 4, so only 2 are there. So the local rank is 4, so 0, 1, 2, 3 over there. So we have 4 processes, 4 GPU, and 4 processes are running on these 4 GPU core, and 4 are running over here like this. So 8 like this in total in this example. So all reduce means that the the uh, aggregation of data will happen, and then distribution of the result will happen. So this will happen for all the processes as such. Like if you can see that we have this MPI underscore sum, so it will aggregate all the values and then it will distribute the results back like the average of the gradients, so they can optimize the the network over there. Now, what is all gather? All gather basically gathers data from all the processes on every process. So here we have these 1, 2, 3 processes like this 0, 1, 2, 3. So you can say that we have this orange data chunk. This is something else. Another data representation is being done with this third color. So basically what happens, the data, everybody talks to everybody, and then the processes basically will get all the various values from the other layer. Now in the broadcast, one of them will broadcast the value to others. Right. So this broadcast is something which we'll also be using in one of the steps. So broadcast data from one of the process into every other process. All of these are fundamental concepts inside the message passing interface MPI. And the open source implementation of MPI is called as Open MPI, like that. So this MPI is something which Uber also found to be very useful for their purpose. So they picked up the data parallel execution mode. They picked up the ring all reduce mode, and they picked up the MPI. But they didn't pick up the MPI which was open source. They picked up the MPI from NVIDIA. So NVIDIA basically has this library called as NVIDIA Collective Communication Library, NCCL. So they picked it up. This is, even you can say, it's the fastest communication, the most HA type of communication. If some communication fails, it will retry and so on and so forth. Everything is inbuilt inside that. Now what it does, the NVIDIA's NCCL library basically does the most optimized ring all reduce at that point in time. Then it was NCCL1, and then NCCL2 also came out afterwards. So they pick that up. So they have, so Horovod is built on three fundamental features or three fundamental ideas, that we will have MPI, massive passing interface will be there from NVIDIA. Then the second thing will be the data uh, execute in with data parallel in data parallel mode. And the third feature was the ring all reduce. Now, if I just walk you through the pseudocode of any typical Horovod example, right? This is how it will be looking like. This is any typical example. So if you remember that we were just discussing that Horovod was like, there are two questions which I was just showing you, that how easy will it be to convert any existing code into something which can be executed on multiple GPUs? Secondly, how fast will it be? There are two main statements. So let's see about the easy part, like how easy it will be, because how fast it will be depends on many things. Like we really have to do a benchmark for you, but there enough benchmarks are available, like 40% faster, 60% faster, and so on and so forth. But for your own particular use case, there will be a benchmark which we need to check for. Okay, now first of all, we have to initialize the Horovod. That's one of the things which we need to do. Now then, this is the local rank. So local rank with a number of unique processes which were there inside the one server. So based on that, so what we are doing is, if you look at this pseudocode over here, we are the one GPU is getting you can say assigned to one to run one process, like that. So if there are 0, 1, 2, 3, then 4 processes are running inside my server. So you can specify things in this manner. Now you should also have a training data set. So get your training data set. Now, but because we have a training data set and we are working in the data parallel execution mode, we have to distribute the data. So in Horovod, there is a particular distribution mechanism called as distribute sampler. What it does, based on the number of you can say sizes and the rank over there. Size is the all total number of processes, and rank is the unique process IDs. Based on that, it will partition your data. It will distribute your data to all the so we can do some we can work it with it parallelly. Now, if you're using PyTorch, then data loader will be there. If you're using uh, any other library, then some other type of data loader might be there. So this is coming from PyTorch. Okay, so we have to build the model. There is nothing of Horovod over here. So in any use PyTorch, use TensorFlow, anything to build your models. Then finally, the optimization which you are going to do, if you're using any type of optimization algorithm, like you're using maybe stochastic gradient descent over here, then the mandatory thing which we have to do is we have to wrap this inside the wrapper. So if I just put one hash over there, So we can say distributed optimizer, and then that one has to be wrapped inside it. Okay, now after that, the when we start uh, with the distributed training of the algorithm on different GPUs, on different nodes as such. So the broadcast happens. So why do we do the broadcast is, if, for example, let's say if you're starting from the scratch, then on day number one, the one of the worker will be broadcasting what everybody has to do, so everything remain consistent, something doesn't go inconsistent. And if there is any checkpoint and you have to start from the checkpoint today, then also it makes sense, like some one of them will read the checkpoint and will inform everybody, okay, this much has been done, let's do it from this point onwards. So there is a broadcast of the parameter which happens from the rank 0 to all the processes. This is what I was showing you a few minutes back, so which we do, and then it's a normal model training which happens over there. So if I just zoom out for you, in Horovod, basically we have initialized it. We are specifying how many process will run on that CPU. This training data set is you can have. Okay, so let me check my audio. Okay, great. I was using a wireless mic earphone. I think forgot to charge it. Now, we have this initialization and we have assigned the processes to the GPU cores as well. Then the data was supposed to be distributed. So we'll just put some number, let's say 1. We have to do this 2. Third, you have to distribute your data. Then you don't forget to wrap the optimizer on top of the, you have to wrap it inside the Horovod distributed optimizer over there. Fourth, and then basically we have to broadcast few of the initial points. Like these are 5 changes which needs to be done on your existing data, on your existing code for it to be run by Horovod in distributed manner. Now, I just want to show you one more thing. So this is what we will be doing today, right? But there is one more thing which I just want you to have a look at this. We have PyTorch Lightning as well. PyTorch is also having another, you can say there is another library called as PyTorch Lightning. Torch is one and PyTorch Lightning is another one. In PyTorch Lightning, it's just one line. That's why it's Lightning, right? So just one line of code. So this is also very useful. But today is not the day of PyTorch Lightning. We can cover it in some other day, but in, you can say, in one line of code, it just does what 5 lines did there. Okay, now if I just take you to the main part. Okay, so now comes Spark. What we have done is, see, you Spark is anyways a parallel distributed compute engine. It run things parallelly as such. Now if I give you a walkthrough of that, like how does it look and feel like? Because today we are working on Databricks. Databricks is a Spark cluster. So how does Spark work? That's what we want to go through once. So I'll just put Spark here like this. So any typical Spark architecture, right? You will submit your application. So that's where you are and you submit it, right? Now so Spark is using Yarn, the clouds they're using Yarn cluster manager. Kubernetes cluster manager is not yet very popular in the clouds. You can do it on premise and so on. Suppose we have done previous sessions on it as well. So anyways, this is Yarn. So Yarn is having 2 of the components over there, the resource manager component over here and the node managers like that. They are communicating with each other. So what happens when you submit your application, the resource manager will basically find the appropriate node manager and will say that go and deploy the driver, the app master. So what this node manager does, let me put some number 1 over there. Sorry, 1 is already done. So let's say 2 right over there. So the third thing which happens is this node manager goes and just deploys this container. Inside this container, we have the application master, the app master, this one over there. Container is not Docker container, don't get confused. This is app master. Inside the app master, we have driver. Inside the driver, we have the Spark session. Everything happens inside the driver. Driver is the most important thing. Here, all the logic will execute. Now, once this has been created, basically it will negotiate for resources. It will go back to the app master, and then it will say that okay, I'm looking for. It will go back to the resource manager. It will say I'm looking for the resources. I want this much CPU core. I want this much GPU core and this much RAM and so on and so forth. So the resource manager, which is anyways talking to all the node managers, will also have over the heartbeat, will know where the resources are available and so on and so forth. So we will be able to schedule that. Now, so at as a response of it, it will get the container leash tokens like that. With the container leash tokens, these drivers will basically go to the node manager saying, node manager, I have the container leash token with me, do this for me. So this node manager will start, you can say deploying more containers as per the requirement over there. Now, this container which we now have created, where the new ones, this is where the task will execute. You see this, the green part. This is called as task. So everything which execute here. Now, one thing which you will remember from Databricks point of view, this architecture which I just explained is open source Spark architecture. In Databricks, we only have one executor in one worker. So one executor in one worker like that. They have their own way of working, so they have kept it like that. So this diagram will be simplified for them. So what is this task? This is where the good thing happens. Now, please notice this. So if I have a job, my job will be broken into stages, and stages will be having task. So you saw those tasks which I was coloring over there in green color. This task, right? These tasks. So they were getting executed in those executors over there. So normally when Spark works, this is how Spark works, like job, stages, task, and then the task will be running. They will not be depending on each other. They will be independent of each other. They will be executing in parallel as such. Now, one thing which I want you to remember, let's say there are three tasks which wants to run, and I have only two slots available. Only two slots are there. Three is not there. Then that's fine. It will still go ahead. One of them will execute later on. So remember this point. So there is no, they don't have to start at the same time. They don't depend on each other. They are supposed to run parallelly to each other. They are independent. They don't share anything. If anything fails over there, let's say one of them failed, then only one of them will be retried, the one which failed. For 4 times by default it will be retried. Then you will get a bigger error. Now, so this is not suitable for distributed deep learning, because if I take you back to the example which we are doing, we have to do ring all reduce. So if you think about ring all reduce, everybody needs to work together. See, if I just take you back to that the diagram which we have kept over here, so everybody needs to work together like that. It's not they have to start if there are multiple tasks. So if I just simplify this diagram saying that I have these tasks over here. So let's say this is one, this is two, this is three. So they have to start together. These tasks cannot they depend on each other. They are not independent of each other. They depend on each other. They are supposed to start together. So Apache Spark was not suitable for distributed deep learning by MPI communication by Horovod. It was not suitable. So what Spark did, so Spark created another execution mode. So the execution mode which I just talked about is called as map reduce execution mode. So the new one which they created is called as barrier execution mode. Now in versus the map reduce execution mode, which is not suitable for deep learning or distributed deep learning, in barrier execution mode, all the tasks will start together. So over here. So if I by chance, if I have two slots and three tasks, error will come. It will not execute. It will wait for three slots to be available, three threads to be available, three cores to be available for it to be executing over there. Now, so if I just put your attention to this point, so in the Spark's barrier execution mode, which is suitable for distributed deep learning, the tasks are supposed to start together. They will be talking to each other using the MPI model, which we understood: broadcast, all reduce, ring all reduce, right? They will communicate with each other if one of them fail, everyone will fail. So if one of them fail, then the full all of them will be retried. It's not only one, because they are supposed to work together. And they will be sent, you can say, ring all reduced manner. They will be sending some data to the next, one of the worker will be sending data to the next two in the sequence. So this is something which is different from the previous one. And for distributed deep learning, that's not going to work out. We use barrier execution mode in Spark. So the RDD is also different. If you have taken any of my previous sessions as well, or if you already know about Apache Spark, we have resilient distributed data sets. But in this example, there is a concept called as RDD barriers. Now, what is this barrier RDDs? Here, the same concept is applicable. That the RDD which is there, it's a special type of RDD over here. Now, that spatial type of RDD will be having some partitions over there, and the partitions will be executing on those various tasks as such at the same point in time. So data will be distributed, but the execution starts together. Everybody works together. Okay, now when we work on Apache Spark with Horovod, there is a particular wrapper which we require called as HorovodRunner. What this runner does, it it basically makes the Horovod run on Spark. That's what it does. So if I just give you the view of it, right? How does it look like? Now, if you think it through, so this is the barrier execution mode. So if I just put some numbers over there, so when you will submit your Python code, the deep learning code as such. So when you will submit your code over here, so let's say this is your Python file. This is the one where we are doing the deep learning over there. Now, when we do that, so and it is using Horovod, right? That is wrapped inside the runner. Now, some particular steps will happen. In the driver, which we were talking about as part of the app master, in the driver, pickling process will happen. Your code will get pickled. That pickle file will be distributed to other workers. So let's say it is getting distributed over here. Then one of the executor, like first executor, zero executor, will start collecting the IP addresses of the other executor wherever they are running as such, because the communication needs to happen. Then after it has collected the IP addresses, it will trigger the MPI based execution. So the data will be distributed and the instructions will be distributed, and then ring all reduce will start after that. So barrier execution mode plus Horovod runner is how Horovod runs in Apache Spark. So today what we are doing is, if you also do that example which I have given in the chat window, right? In that we are doing the same thing. So this is my Databricks Spark cluster in Azure. I'll walk you through this. So I went to my Azure portal and I have created one Databricks cluster over there. This one, my Databricks workspace, and basically I created one premium type of workspace which will provide me with the Azure Active Directory integration, which is over here. And it will also provide me with the credential pass-through, which is a very nice feature, but it's not the focus for the day. So I made the premium workspace. I have opened it up over here. Okay, then I created the cluster over there. And I have one GPU cluster which is running right now. And one CPU cluster is terminated because of auto scaling. It's scaled down to 0 instances and so on and so forth. So let it be terminated. And if I just click on it, so you have to give the cluster mode. Cluster name, we have various type of modes over here: single node, standard, high concurrency. So this is like a single user cluster. This is basically the shared cluster over there. You can make any type of cluster, but when you do this, you go to the Databricks runtime, click on the machine learning runtime, go for the GPU runtime over there, like this. So I have created one GPU cluster over here. It will work with CPU also, but if you want to see how fast it can go, you can try the GPU version as well. So I am going for the long-term support machine learning version on GPU. And then I have kept it on auto scaled and so on and so forth. And there are various sizes which are there. So your subscription should have the quota limit. So my cluster is already running, but if I show you the GPU sizes, it's over here. These NC series are there where you can see 2 GPU, 4 GPUs, 448 GB RAM and 4 GPUs and so on and so forth, like that. So select the one which is suitable for you. That's the driver type. So this is the driver where that pickle process will happen. The workers are workers as such, where executors are there. So this cluster is running right now, that cluster which we are using. And that's my, I went to the workspace after that. And in this workspace, I have created one. Uh, I have actually imported the notebook, but you can create it from here like that. So this is the training code over there. So if we recall what we have covered, right, we have to initialize the Horovod library. We have to specify that how many process will run in 1 GB, 1 GPU, and we have to distribute the data. We have to wrap the optimization algorithm in the Horovod wrapper. Then we basically, once we have done all of this, we will be broadcasting the initialized, or you can say initial starting points, the starting variables, and then we have to do the normal machine learning training after that. Any normal execution mode will be there. So what we are doing in this is we are training a convolutional neural network. So convolutional neural network is basically one of the simpler type of deep learning architecture, which generally I also use in a lot of my examples, and which is easy to explain also. So I also, so because of that, I also use it. I will spend 2-3 minutes into going through few of the fundamentals of it, and then I will just walk you through the the pseudocode which we have understood earlier, and we want to see that. So basically, convolutional neural network works in this manner. We have convolutions going on, and pooling layer is there. Now, there are multiple use cases of CNN, convolutional neural networks. They are used in medical fields. They are used in object tracking. They are used in OCR, optical character recognition. They are used in semantic segmentation of images as well, like that. Now, the problem is when you work with images and when you have a lot of images, they will take a long time to train. So instead of that, we already have understood that how Spark works. With barrier execution mode and with Horovod, HorovodRunner, which is using Horovod, we will be training the convolutional neural network on multiple GPU cores as such. So in convolutional neural network, there are basically convolutions are happening over here. So convolutions are these operations where the filter is moving over the input image in this manner, and metric multiplication is happening and you're getting some output over there. So it depends on your image also, like how many channels do you have in the image? Like is it having, is it RGB or is it having one channel only? So based on that, uh, you can say the filter will be there, the kernel will be there, it will be uh, moving around the input image or in the feature map, like whatever output will come, whatever channels output will come, the next uh, kernel will run on top of it. So you see what is happening right now. We have that RGB image, and that kernel is also having three planes over there, and the kernel is having three, we can say, the kernel channel 1 is running on the red one, and the 2 is running on the green one, and the 3 is running on the blue one, and we are finally getting one output channel over here, which is the combination of all three of them. So during the convolutional neural network training, we are learning the weights of these kernels. If we learn them properly, we'll be able to work on them uh, as such in a manner. So in the code, we will be using ReLU as the activation function. This activation function basically will be reducing the negative values to 0 over there. It will you can say diminish the non-dominating features, and it will literally make them 0. We also will be using max pooling, and max pooling means that like whenever you have, it's the most dominating feature which is there. That dominating feature is what goes in the next one. So if you can see that 8 is the one which goes in the output channel when the max pool is done on top of it. Similarly, we also have other things in CNN. We have average pooling as well. and average pooling will take the average of that section of the feature map, and then we'll throw the output. So convolution neural networks looks like that. We have various convolution layers where the filter is moving over the input image, and then we have the output images are there. Sorry, the output feature maps are there, and then we do the pooling on top of it, more convolutions. So it's basically what we are doing is feature extraction. We are extracting the features from the image. So for example, there is a very popular convolutional neural network called as VGG16. That VGG16 it picks out 4096 features from every image. As such, there were millions of images, but 4096 features were extracted from every image. So this is VGG16. This is what I have uh, over here. And if I just take your attention to this point, so there were 1000 classes, and we are doing a classification right now, but the 40996 features were extracted from the input image, like that. So all the images will have these many number of features over there. Okay, so if I take you back, and we now just have to implement this, right? So I'll just take you back to the pseudocode, and we will keep that open, and we will realize from that point onwards, like what do we have to do over there. Let's put this over here. Okay, so check this out. Now, yeah, so we start from the, okay, let me show, sorry, let me show the CNN creation as well. So this is where we are creating the convolutional neural network. Whenever you, and we are using PyTorch right now. So when you work with PyTorch, basically when we create when we create any neural network, we have this, we have this class net, and we have the forward function over there. We initialize, and we have the forward function as well. So how many layers are there, how the layers are constructed, that is the initialized one in it over here. The forward means how the data will be passing through them. So we define them in separate two different, that there is a one method and there is one class, and it is having two different, you can say, functions are there, and these in the forward and in the init we are defining it. So we are using the convolution neural network. It's 2D convolution which is going on. The kernel size is 5x5. The input channel is only one, and we are applying 10 kernels over there on the input channel. So when the output comes, we have to anyways, now we have 10 of them, and the kernel size is 5x5 and then 20 this time. Then if we don't want to do any type of overtraining, then we are doing the dropout over there, and then we are sort of we are flattening the output, and finally 10 classes are there. The data set which we are using is called as MNIST data set. MNIST data set are having digits, handwritten handwritten digits are there. If you think it through, how many digits are there? 0 to 9, right? With the 0 to 9 digits, you do all the combinations. So 10 classes are there. So handwritten input features, and then they need to be classified in 10 outputs. So this is the convolution neural network which we have created. And now we don't want to do the single node training, but we want to use HorovodRunner to do the distributed machine learning. So if I take you to that main part, check this out. Okay. So we will initialize the Horovod. If you have CUDA is basically if you have GPU, use it, otherwise CPU. So we have GPU with us, otherwise it will use CPU. Then the local rank should go there. Right? I think is not on mute. Okay, check this. So what we are doing is one process for one core, we are using the local rank option, which is there. So local rank means how many how many GPUs were there on one server. This is a PyTorch snippet over here. Like data set is like MNIST is a type of data set which is there. And this is wrapped around another one called as data loader. Somewhere will be here. And data loader is the iterator. It will load the data in some batches. So, but we are working in distributed manner. So we are using the distributed sampler of Horovod, which will, you can say, will create the chunks out of my data. And then the optimization algorithm which we are using needs to be wrapped around the Horovod distributed optimizer. So it can do that ring all reduce operation. In that manner, the communication can happen at the backend, and we are basically sort of broadcasting the initial parameters to all the workers. So one of them is broadcasting it, and then normal machine learning model is getting trained over there. So uh, okay, and we are able to achieve some test loss and accuracy and so on and so forth as well on top of it. So if I take you back, so with more or less with five line of code, you will be able to run your existing single core, single node, non-distributed deep learning PyTorch or TensorFlow code into distributed mode by using Horovod. If you use Spark, you need a HorovodRunner, and in Spark we are using the barrier mode, which is basically by default over there. Without it, it will not work. So it will be written somewhere over here that we are going to use the barrier execution mode of Spark to be able to do this. So this is what I had for the session. I'll just take your questions, and if you think it through and let me know what questions comes to mind. Okay, so I'll keep this page open over here. Right, so a quick recap will be barrier execution mode for Spark, data parallel execution mode, MPI communication concepts as such, and the NVIDIA NCC L2 library, which is the optimized version, and run it on Spark. And Spark is anyways, you can say, can use GPU and CPU and so on and so forth. Run it on the cloud in a cluster like Databricks, which is a type of a Spark cluster, and you get best of all the worlds together. And you will be able to execute you will be able to convert your existing single code deep learning uh, snippets into the distributed one. And if you use PyTorch Lightning, then in single line of code, you can also do that. So that is something which we can also remember. Okay, so can you show the processing time with or without Horovod? So I will show you that. Okay, so what I'll do is I am giving you the benchmark which they have created in the chat window on their, you can say, on Horovod's own page. So on this page, I think it's on the bottom of the page over there. As such, somewhere here, where the benchmarks are there, like when how many, let's say how much percentage, like how fast it executed. So in percentages, you will find the output as such. Like when ResNet was trained, it was trained 40% fast. When Inception v3 was trained, it was trained some X amount fast, like that. So like exceeds 90% scaling efficiency for both the models, like that. So use this page and all the benchmarks are there. Right. So now which one is better, Horovod or Ray for deep learning? I don't have any comment to make in that. I also use Horovod and TensorFlow distributed, Horovod, both of them. Horovod, sometimes it's easier to work with, as you already saw that. PyTorch is the go-to framework, so it works very well with it. Okay, so as part of the session, the learn module is there. Whatever we have done, it's over there. It's even more in a way more structured manner. And the recordings will be available on the I'll give you the link in the chat window. It's on YouTube, and you can simply join that channel over there for the previous recordings and for future recordings also. Can you also provide the implementation of the HorovodRunner? HorovodRunner is a simple, you can say, it's just like this. First of all, it's there in the link which I gave, but if I just show that to you as well, we have to import that. So I'll just take you few snippets back. This is single node. So let's go over here. That's all, like this. So you need to initialize it like this. Okay, so go with it, guys, and try this out. Link is in the chat, and have a nice day. I'll see you in the next session. If you have questions for me, feel free to find me on LinkedIn platform or any other social media platform. All the links are there in the meetup page. The recordings will be on YouTube. Please join the Reactor page. It's also in the chat. And join the Reactor group on LinkedIn so you can be in touch when we post there is a session tomorrow also. Join for the tomorrow's session as well. And for other sessions which are going on, you have to join on the meetup page, or on LinkedIn you can join the Reactor group as well, right?
Thanks, Shivam, so much for the session, and thank you all for joining us today. Please share your feedback about today's session, and please visit our Microsoft Reactor Bengaluru meetup page for more upcoming session. Thank you all once again.
Thank you, everyone. Thank you, Rashmita.